Okay, so first section is tech-free. Sketch the graph of f on the axis below, label the axis intercepts with their coordinates, and label any asymptotes. All right, so we should be able to look at this graph and identify straight away that I've got x equal to 1 is a vertical asymptote, and y equal to 1 is a horizontal asymptote. So we come over onto the top of the graph, y equal to 1, horizontal line, put the dotted line in, x equal to 1, vertical line. Try please use rulers, boys, because it is a straight line. So you need to be as accurate as you can. All right, so there's your first two parts. Hopefully we realise that we're in the top right quadrant and the bottom left quadrant. And so we need to find our intercept. So if we come to the middle, the y-intercept, x equal to 0, just put 0 into the equation. I get the point 0, negative 1. X-intercept, put y equal to 0, solve the equation. So at this point here, we get negative 1 equals 2 over x minus 1. Mathematically, you multiply the x minus 1 across, and then you bring the negative 1 back on the left side, back onto the other side. Or you could just flip both sides upside down. You know, there's a couple of ways, all right? But you have to take the 1 across first, all right? Then you end up with our x minus 1 is equal to negative 2, x equals negative 1. So if you put those points in, you can see over here on the graph, little red dots there, label the coordinates, and sometimes it gets a little bit tight. So we get that graph drawn there nice and accurately. On the right-hand side, or the upper limit, the upper quadrant, we really do need to have a point. Examiners don't like it if your graph is nothing like what it should be. Okay, so label a point. So I've just picked a nice number here. I've just put x equal to 2, say x equal to 2, substitute, I get the point y equal to 3. So whether you just put a point there, if you label it, there's nothing wrong with that. But at least it gives you an idea of how steep the graph should be, where it roughly should be. All right, so do that. Your teachers and examiners will love you. State the rule of the domain of the function of the inverse. Okay, so we've got the actual function here. So the domain of the inverse we can do straight away because that's the range of the original, isn't it? And the range of the original is R except for 1. There's my range, the y values. So that's where that comes in. Mathematically, to find our inverse, come back down to B. So F inverse, swap X and Y. So again, I'll take the 1 across first to get X minus 1. Again, you can argue mathematically, I'm going to multiply that across and then bring the X minus 1 back on the other side, and I end up there. Then if I add 1 to both sides, I'll end up with 2 over X minus 1 plus 1. Don't forget, last line, F inverse is equal to. Too many of us forget that. That's going to cost you a mark. And we don't want to lose marks where we don't have to. All right. Find the values of x, hence find the values of x for which f of x is equal to f inverse of x. Now, immediate response is to say they're equal along the line y equals x. Yeah, if they reflected about that line y equals x. And that's true. If I put my, it will be true. But what we also notice is the two equations are identical. So they're true for all of those values, except for, of course, at x equal to 1, where the function isn't defined. Okay, so that was a pretty nice sketch graph. Let's come down, we've got our transformation. The graph of f is shown below. The point P lies on the graph of f. Y equals f of x, which is root x. The point Q10 lies on the x-axis. The transformation T maps a graph and it becomes a function h of x. So h of x is my new function. Show that the point P10 lies on the graph of h. So what we're really looking to do, I want to get a rule that says h of x is equal to, substitute in x equal to 1, and hopefully get y equal to 0. All right. So let's consider my transformations. There's my transformations here. So x dash is equal to x, y dash is negative 2y plus 2. Rearrange, so I can get x is equal to x dash, y is equal to y dash minus 2 on negative 2. That's x equals y equals. I now know, since y equals square root of x, I substitute those values in. So I guess technically I should have a little dash in here. Put a little dash there to be consistent. Once I get there, multiply the negative 2 across first, then add the 2 over to give me h of x is equal to negative 2 root x plus 2. That's my new function. Notice it's h of x. That's my new function that it became. Now if I put x equal to 1 into that, I get negative 2 times square root of 1, which is negative 2 plus 2, which is 0. So the 0.10 is on h of x. All right. A little bit of trig. This was a past paper question, so you can see the level of maybe tech-free solving trig equations we may be asked to get to. Solve 2 f of x minus 1 equal to 0. F of x is sine x between negative pi and pi on 2. So if I rearrange, I get 2 sine x minus 1 equal to 0. 2 sine x is equal to a half. So my quadrants, first and second. So the angle of interest is pi on 6. So then my first solution, pi on 6. My second solution, 5 pi on 6. I could come all the way around to go to 6, 7 pi on 6. Or if I go from 0 back negative, I get negative 7 pi on 6. Now, my domain is from negative pi to pi on 2, so pi on 6 is the only solution inside the domain. One marker, very nice. Now sketch the graph of y equals f of x. Oh, sorry, the graph of y equals f of x is shown below, which is f of x is equal to sine x. Sketch the graph of 2f of x minus 1. So what happens with those? You can see there the two different steps. So dilate by a factor of 2 from the x-axis. So you can see there, the y values get multiplied by 2. So in blue, I've just brought everything down. So that's the interim stage there. And then I shift the whole graph down 1 unit. And so in yellow, that's my final graph. Every point moves down 1 unit. All right. So what are my new? Label the endpoints of the graph and the axis intercepts. The axis intercepts, 0, negative 1 is what we've just, is the intercept because we moved it down 1. The x-intercept is what we solved from the previous question. So it's a bit hard to read in there. So that x-intercept is pi on 6. 0 coordinate, endpoints, just substitute pi in, or negative pi I should say, but even the endpoints you can map, can't you? Because you just moved everything down. Negative pi, negative 1, pi on 2, positive 1. All right. All right, so let's have a look. Consider the function negative infinity to b is the domain for f of x equal to 5 minus 4x minus x squared. Find the largest possible value of b such that f is a one-to-one function. So first thing there, I guess the most significant thing there, one-to-one function, all right, which means we know that a quadratic has a turning point. So we want to know what the graph looks like and basically know where the turning point is. A number of ways you can find a turning point, boys. You can use your minus b on 2a. Complete the square is the way I'm going to do it. So for me, if I take that negative sign out the front, I change the sign on everything inside, okay? So remember that if you're going to complete the square, it is x squared plus 4x, half the middle term and square it, subtract half the middle term and square it, and then I have minus 5 at the end, yeah? So that there is x plus 2 all squared minus 9. Negative sign out the front gives me that expression there. I'm feeling comfortable with that because if I sketch that graph, I've got a turning point at negative 2, positive 9, so it's upside down. And if you come to the top of the page, you can see there that for that function to be 1 to 1, we need to stop our domain or start our domain at -2. So we either go to the right, -2 to infinity, or we come from the left, -infinity to -2. All right. And since we need to do -infinity to b, we're going to go -infinity to -2. Find the inverse function. All right. So if I run with the function as it is, a lot of us will try and do over here on the right hand side, if I try to do y equals 5 minus 4x minus x squared, and then we'll go x equals 5 minus 4y minus y squared. And we've still got y in two places. So if we've got our quadratic, we need to get that factorised. So the advantage of completing the square in part A is I'm going to start with, if we come back to the question, I'm going to start with it in completed the square form. So now if I swap my x and y, I've got one x, one y, I can rearrange everything more easily. Bring the 9 across first, then divide by the negative. Yeah, well, it's not order of operations, just transposing. If I've got x is equal to 3y minus 2, if I divide by 3 first, I've got to make sure I divide everything by 3. Including the 2. We tend to forget that. So it's easier to do the subtraction first. So we get 9 across on the left-hand side, divide by the -1. So it becomes positive 9 negative x. Take a square root, so we get plus or minus, y plus 2. Take the 2 onto the left-hand side. I end up with -2 plus or minus 9 minus x. You need to make a decision about whether you're going to have the plus or the minus. So if I go to the range of my original function up here, we can see that the range is from 9 down to minus infinity. So from -infinity to 9. So I get these big negative values. So that's what I'm going to have in here. I'm going to keep the negative sign to make sure I get these big negative values. Yeah. So we end up with f inverse of x equaling -2 minus square root of 9 minus x, where x is an element of -infinity to 9. Keep sliding through, express f in the form a plus b over 2x plus 3. So we need to do, typically we do our division. We can do repeated factor and things like that. I might do one of those in a minute. But typically we've got 2x plus 3 going into, I'm just changing the order slightly, -2x plus 3. So don't forget that the negative sign belongs to the 2x. So in red there, we've got a -1 at the top, multiply it down, we get -2x minus 3, subtract 3 minus 3 is positive 6. So it goes in -1 times plus 6 remainder. So plus 6 over 2x plus 3. So now we need to state the values of A and B. A and B are -1 and 6 respectively. Capital D is the domain that we're interested in, which we've got R except for -3 on 2. If you want to just do it like a repeated factor method, you could write 2x plus 3. We won't need it twice, but we'll do it twice. And we have to end up with -2x plus 3 as my answer. So if I put a -2 out the front, if I put a -1 out the front, I'll get -2x minus 3. So the -2x matches. And I've got -3. I meant to have positive 3. So I need to add 6. Yeah, so that gives me -2x plus 3, which is what I'm after. So my answer is -1 and my remainder is 6. So -1 plus 6 over. So you can still use your repeated factor method to get into the form that you need. All right, our hyperbola. Sketch the graph on the axis below, label asymptotes with their equations and the actual intercept with their coordinates. Straight away I can see I haven't quite finished everything. So I've rewritten the equation somewhere, have I? I have. It's over here. -1 plus 6 over 2x plus 3. So straight away, put my asymptotes in. So I've got y equals -1. So there's my horizontal asymptote. 2x plus 3 is equal to 0. So 2x is equal to -3. X is equal to -3 on 2 is my vertical asymptote. So I've labelled those okay. Next, find my intercepts. I come to the right-hand side. If I put x equal to 0, I get the two x's are both 0. So I end up with 3 on 3, which is 1. So let's label 0, 1. So I better put the coordinate in because I forgot to do that. And then if I put y equal to 0, well, the only way, if I've got a quotient, the only way you can get 0 is if the top line is equal to 0. So 3 minus 2x is equal to 0, it means x is equal to 3 on 2. So 3 on 2, 0 is my other intercept. So that gives me that top right corner pretty clearly. I've mentioned previously, let's just pick one point for a dilation factor, just so you know roughly where it's going through. So that's what I've done over here on the right in blue. If I just put x equal to -4, so I try to pick numbers that I know will give me easy to work with. I put x equal to -4, I get 11 on -5, so -2 and a bit. So that's what I've marked in here. I've just marked a point there at about -2 and a bit, just so I've got a rough idea of how close to the line I am and where I might start turning and all those wonderful things. So let's check, sketch the graph, label all the asymptotes with their equations. We did that. Actual intercepts with their coordinates, we've done that. Okay, problem done. Y is equal to g of x, which is 6 sine 2x minus 4 plus be a function of time by applying the transformation to y equals f of x equal to cos x, where the transformation is given by ax plus hby plus k. Find the values of a, b, h, and k. This is a tricky question, all right? And I found the nicest way to do it is if we consider the function that we've started with, because what we're looking at is we've got to turn the sine function into a cos function. And so we do know that we have sine theta, and we can have pi on 2 minus theta is equal to cos theta. So we do know that to turn a sine into a cos, there's that pi on 2 theta sort of a shift, isn't there? So if I stay over here, actually, if I've got my y is equal to, and I've written it over there, 6 sine 2x minus pi on 2, if I multiply that through. So if I want to write it in exactly the same way, 6 sine, let's put a negative sign there, and I can go pi on 2 minus 2x. Well, that's my pi on 2 minus theta. So I can write that as 6 cos negative theta, or sorry, negative 2x plus 3, which is negative 6 cos 2x plus 3. So I haven't done any transformations yet. I've just used that compound angle formula, okay? So that's what I've ended up with here in the second line on the left. I've rewritten my function as negative 6 cos 2x plus 3, and now it's really easy to compare it to the cos x function. So I've got y is equal to, so let's bring the 3 across from negative, divide by negative 6 equals cos 2x. So this is the function obtained by applying the transformation. Yeah, so I turned cos x into that. So this is my new function, which is why I've got the dashes there. So again, I've got y dash minus 3 on negative 6 is equal to cos 2x dash. So y is equal to, x is equal to, x dash is a half x, y dash is equal to negative 6y plus 3. So if I put it in the form that I need, so really I'm saying then the transformation of x and y can be written as half x, negative 6y plus 3, and I can use that information to marry off with my A, B, H, and K. All right. So the trick I really think for that one was to work out how sine can become cos. All right, so with our transformations now written in our t of xy form, we can see a half of x, so we halve the x coordinate. So it's a dilation by a half from the y-axis. 6 in front of the y, dilate by a factor of 6 from the x-axis. A negative y, so we're going to reflect about the x-axis, and then we translate 3 units up. All right. Part C, sketch the graph. On the axis below, label the coordinates of all the actual intercepts and turning points and endpoints. So we can certainly sketch it transformation at a time. As soon as we move vertically up, though, our x-intercepts change, so we're going to have to solve the function for that. So let's do that first. So if I solve h of x equal to 0, it means sine of whatever the angle is equal to negative a half. So we know that sine is negative in the fourth and third quadrants. So by 7 pi on 6, by going around in a positive direction from 0, come into the negative direction from 0 to get my next one is negative pi on 6. So I've decided to get my first two solutions, divide both sides by 2, make some 12s, add 3 pi on 12 to both sides, gives me a 10 pi on 12 and 2 pi on 12. Okay, so they're my first two solutions. The period of the graph, so the period is 2 pi on 2, which is equal to pi. So I'm just going to add 6 pi on 6 to all of those solutions to get the other ones, add and subtract. So 5 pi minus 6 pi on 6 is negative pi on 6. Pi on 6 minus 6 pi on 6 is 5 pi on 6, or negative 5 pi on 6. If I add pi on 6 on 6 to pi on 6, I get a 7. So 7 pi on 6 would be the next one up. And that's outside the domain, so I don't have to worry about that. All right, so they'll be my 4 x-intercepts. So I know it looks a little bit messy down in here, but I've tried to do a bit at a time. So the green function initially, I'll keep a red pen. The green function initially is 6 sine 2x. So again, I know the period is pi, amplitude is 6, so let's just draw that. So if you have a look in the green, you can see, I'll just go over it, up to 6, and I've got a complete cycle done by pi. All right, so that's that one. I then wanted to shift pi on 2 units to the right, so I've done that in yellow. So each intercept has moved pi on 2 to the right. So that yellow one, if I look at the, it's a bit tricky, look at the graph again, do a circle around it. That yellow intercept would be at the point pi on 2, wouldn't it? Because I've moved from 0, 0 to pi on 2, 0 to the right. So now in the yellow, okay, I've shifted everything to the right pi on 6. To the right pi on 2 units. And then finally in black, I've moved everything up 3 units. And that's why my intercept changes. All right, so you can see in black now, I probably could have just tried to do that by video. But I'm just going over the black, not that there's much point. Everything's moved up. So I've got my x-intercepts, negative pi on 6 and negative 5 pi on 6. Looking at the graph, that looks about right. We can see our maximum up there at 9 and our minimum down at negative 3. What do we have to do? Label coordinates of actual intercepts, we've done that. Turning points, we've done that. And endpoints, make sure you do that. So please, at the end of each question, go back and check. So as I'm making the video, I've already found one mistake there in the first question. All right.